Okay, so we're into section 4 of chapter 9, and just so you know, we're going to spend probably more time than anything on these last two sections. The polynomials are important. The Taylor polynomials, Maclaurin polynomials, all those things are important. But also convergence and divergence are very important. That's what we're going to look at in 9.4 and 9.5. All right, convergence, the series that are the most interest to us are those that converge. That means that they are, if you add an infinite number of terms, that sum is still going to approach a certain value. Now, it's never going to get there, otherwise you couldn't continually add things over and over and it not approach that value. It would get larger or it would get smaller. So it's going to converge. The sum is going to approach a certain value, and that's what we talk about when we're saying that a series will converge. Remember, a sequence converges just simply means each individual term goes to a certain value. When we're talking about a series, we're talking about the sum of all those terms of the sequence. Don't get those confused. A sequence is just the list of terms. A series is the sum of those terms. An infinite sum of those terms most of the time. Now, today we'll consider the question, does this series converge? And if so, for what values of x does it converge? So there's two different things. Does it converge? And if it does, are there certain limitations for x values that will allow it to converge and other values of x where it will diverge? Now, the first requirement for convergence is that the terms must approach 0. And that gives us our first test. We're going to have a list of tests. I'm going to give you a list that has all these tests on it. But you want to write these down and show how they work and all that stuff. And our first test is the nth term test for divergence. Now notice this is a test for divergence, not a test to prove convergence. So if our sigma notation of a sub n, it's going to diverge if the limit as n approaches infinity of a sub n, these terms, fails to exist or is not 0. So if we take the limit of this term right here, just this term, ignore the sigma, all we're worried about is that. So if we take the limit and let n go to infinity, if this value, if the nth term does not go to 0 or the limit fails to exist, then this thing is going to diverge. This is not a proof of convergence, it's just a proof of divergence. If we're adding things that are continually going to be more and more and more, or have value and that value is not going to go to 0, then if we keep adding that same thing over and over and over and over again, it's not going to approach a certain value. So if we know that it does not go to the limit does not go to 0, then this thing's going to diverge. Note that this can prove, as I said, that a series diverges, but it cannot prove that a series converges. So this is a quick, easy way to look at it, and it's an easy way to prove a function's going to diverge. And then once you know it diverges, you know it doesn't converge, so you can ignore the rest of it. You don't have to go any further. You always want to look at this thing first, because if you can prove that it diverges, then you're done. And this is by far the easiest test. You just take the limit of this thing as n goes to infinity, and you'll typically be able to figure out what it's going to do. So for example, we have the sigma notation where n is starting at 0 and going to infinity of n factorial x to the n. So what we're looking for here is the nth term test for divergence. We're only looking at that. So what is the limit as n goes to infinity of n factorial x to the n. Well, what's that product going to be? Well, if we have n factorial with n going to infinity, this is going to go to infinity definitely. And x to the larger and larger power is going to go to infinity. So infinity times infinity is just another infinity. So this one does not exist. Now, think about what's going to happen. Just look at a couple of these terms and you can kind of see what's going on. If n equals 0, we have 0 factorial, which is 1, times x to the 1, whatever x is. So x to the 0 power would be 1. And then plus, let's let n equal 1. We've got 1 factorial, which is 1, and x to the n power is going to be x. And then 2, we're going to have 2 factorial, which is 2, x squared, plus 3, x to the third, except that's 3 factorial, so it's 6. And we can see right here, depending on what x is, this thing is going off to infinity. So our n factorial x to the n is going to grow without bound, as long as the absolute value of x is greater than 1. Now, if we have a smaller number, a fractional number, for the absolute value of x, then you end up with n approaching infinity as n factorial over x to the n, and you can move that to the bottom and think of it as 1 over x to the n. So that means this down here is going to go, it's going to get larger and larger and larger, but n factorial is going to grow way faster than that thing is, so we still end up with infinity. So this thing's going to diverge for all real numbers. So as n approaches infinity, eventually n is larger than 1 over n. Therefore, the numerator grows faster than the denominator. Therefore, the series diverges, except when x equals 0. If x equals 0, this thing's just going to be equal to 0. Because we're going to have 0 plus 0 plus 0 plus 0 plus 0. So you always have to think about the different areas, the different aspects of what's happening here. So the reason we had to break this up into 2 parts is because this is what? It's actually an adjustment. It's not exactly a geometric series, but it's close. Well, is it a geometric series? It's going to be multiplied by n times x each time. So technically, no, it's not a geometric series because it's not multiplied by the same thing every time. But we know that the x to the n, if the absolute value of x is greater than 1, then we know that just the x to the n is going to diverge. And if we know that our x is between 0 and 1, the absolute value of that x is, then what do we know? We know we're thinking about it as 1 over x to the n power. Or actually, we're thinking about it as the fraction, and we can flip it over, and that's what we get down here. All right, so there are 3 possibilities for power series convergence. The first one, the series converges over some finite interval, and this is known as the interval of convergence. There is a possible number r such that the series diverges for all values greater than r, but converges when those values are less than r. And the series may or may not converge at the endpoints of the interval. You have to check them. All right, and number 2, the series converges for every x. In other words, the radius, and that's what this big R is, it's the radius of convergence, is equal to infinity. And that's true if the series converges no matter what x is. And then the third option, the series converges at x equals a and diverges everywhere else. And typically what we found, like with that last example, where it's going to converge when the x was 0 and for all other values it diverged. And in that case, where it converges at only one value, the radius of convergence is equal to 0. Because remember, a radius is from the center out to the end point. In this case, there's only one point, which is the center, so the radius is 0. And as I said, the number r is the radius of convergence. So it is going to be the interval, no, it's going to be 1/2 the length of the interval where this thing's going to converge. Okay, the radius of convergence is 1/2 the length of the interval where this thing converges. So what that means is if I had an interval that I knew this thing converged on from, let's say, -2 to 5. Let's go ahead and make it really difficult here. How many places do I have from -2 to 5? Well, there's 7. So that means the radius of convergence would be half that, which is -7/2. Not negative, sorry, 7/2. And that's because at the center, which would be wherever it is in there, it's going to be +1.5, and going from there to 5, and from there to -2, each one of those is 7/2. That's where we get the radius. It's still a radius even though it's along a line, the number line. All right, now we can check and prove convergence in a couple of different ways. Let's look at some of these tests. The first one is a direct comparison test. For non-negative series, if every term in a series is less than the corresponding term of a convergent series, then both series converges. Well, literally we are just checking to compare two series to each other. So if we have a series that is non-negative, in other words, there are no minuses in there at all, if every term of a series is less than a corresponding term of a convergent series, in other words, we're looking at it term for term with a series that we know is going to converge. And if every one of the ones that we're checking, if every term in a series that we're checking is less than that one that we know converges, then both series are going to converge. This is where you're going to use a series that you know converges and compare things. So if we have this one and we know that it converges and the blue dots are corresponding to the red dots and they're always lower, if we know that the red is going to converge, then we know that the blue has to converge as well. So we know the red one converges, and if the blue values for each term, each corresponding term, is less than the convergent series, then we know that the blue series must converge also. Now, if every term of a series is greater than the corresponding term of a divergent series, then both series diverge. So it's the same thing here. It's very similar to what we talked about when we talked about the sandwich theorem, except for in this case we're only using 2, and one is going to determine whether or not the other one's going to converge or diverge. Depending on, and what you're doing is you're kind of sandwiching, in this case you're sandwiching the blue series between the red and 0. With this option here, you're actually sandwiching the blue between the red and infinity. And you know that the red would diverge. So let's look at that example. So here's the red series, and let's say we know that's a series we know, and we know that every one of the corresponding terms in the blue series are always greater than the red series. Now, if this is the one we chose, and we know that it's divergent, and all our blue dots, our blue corresponding parts, are greater than the red, which diverges, that means the blue has to diverge as well. Because term by term, you're doing what? You're adding more value to it. So if this one diverges and you're adding more to this one, it's certainly going to diverge. All right, so prove that the series n equals 0 to infinity of x to the 2n over n factorial squared converges for all real x. All right, so there are no negative terms here. We don't have negatives top or bottom that we need to deal with. And we know that x to the 2n over n factorial squared is going to be less than or equal to x squared to the n power over n factorial. Now, why do we know that? Well, because if we square the bottom, what's going to happen to these numbers on the bottom as n gets larger and larger? We're going to have a larger number in the denominator. If we have a larger number in the denominator dividing into this top, that's the same, by the way. What do we know about this fraction versus that fraction? Well, if we're dividing by a larger number here than we are over here, but we have the exact same values up front, up top, that means this one has to be less than that. The only option where it would not be was if we were looking at an n equals 0 or something like that. So this is the comparison we're going to use. So x to the 2n over n factorial squared is less than or equal to x squared to the n power over n factorial. Now, this over here is nothing more than the Taylor series for e to the x squared, which we know converges. How do we know it converges? Well, it converges for any value of x, it's going to converge to e to the x squared. Whatever x is. If x is 4 here, it's going to converge to e to the 16th power. So it's going to converge for all values of x. So that means that if this thing as it is converges, and this thing is always greater than or equal to this thing, what do we know about that? Well, this is the sandwich thing. If this thing is holding it down, this thing is always below that, and this one converges, that means that this one must converge as well. So since we know that this right here, the series x squared to the n power over n factorial converges to e to the x squared, and this series here is less than or equal to this one for all values of x, then this one's going to have to converge too. Now, the direct comparison test will only work when all the terms are non-negative. So it's not going to work for your typical cosine or sine series or anything like that. All right, now let's talk about absolute convergence. If the sigma notation, or the sum of the absolute value of a sub n converges, then we say that sigma of a sub n converges absolutely. what that means is this absolute value here is taking out the possibility of alternating signs and things like that. So if we take out the absolute value and do the series, that means we're stripping out any negative values that would alternate or subtract away from value. So if the absolute value of a series converges, then we say that that series converges absolutely. Now, the term converges absolutely means that the series formed by taking the absolute value of each term converges. Sometimes in the English language we use the word absolutely to mean really or actually. This is not the case here. It simply means that if this thing converges absolutely, then we know its absolute value of the series will converge as well. So don't read more than that meaning into it. Absolutely is not the, always or anything like that. So be careful about that. Now, if the sigma notation of the absolute value of a sub n converges, then the sigma notation of a sub n converges as well. So if we can prove that this converges, then we've proven that this one converges. So that's another test right there. It's the absolute value test. So if the series formed by taking the absolute value of each term converges, then the original series must also converge. If a series converges absolutely, then it converges. You would hope if you say converges absolutely that converge would be part of it. All right, so let's look at this one. All right, so looking at this example, we have sigma notation of sine x to the n power over n factorial. Now, we want to test, and we'll test for absolute convergence here. And the reason we're going to do that is so we can do the absolute value, because that's going to take out the negative part of this thing up here. If we take out the negative part, we can just look at this as being 1 to the n power over n factorial. Because at a maximum value, sine has a value of 1. So if its maximum value is 1, then it's never going to be greater than 1 over n factorial. Now we can say sine x to the n power is never going to be greater than 1, because if this was a fraction or a decimal raised to that n power, it's going to be smaller than 1. So that's why we can say that. At a maximum value, the absolute value of sine x is going to be 1, and 1 to any power is going to be 1. So sine x to the n over n factorial is always going to be less than or equal to 1 over n factorial. Now, since e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x sub n over n factorial, then this is nothing more than e to the first power. So this 1 over n factorial is just taking the place of the x and putting in a 1 there, right? 1 over n factorial when n is 0, 1, 2, 3, 4, 5. 1 plus 1 squared is 1 plus 1 to the third is 1 plus 1 to the n power is 1. So we end up with 1 over n factorial. So this part over here is going to converge to e to the first power, or e. And what do we know? Well, if that is always going to be greater than or equal to this thing, and this one converges, then we know that that's going to converge as well. Now, you're going to notice here that we're not finding the value it converges to. Don't worry about that. That's not something you do. You're just worried about whether it converges or diverges. Now, you're going to notice here, you're going to have to show your work, show your reasoning, and you're also going to have to tell what test you used. You're going to have to provide all that when you have these problems on free response or written work. So this gives us the since the sigma notation converges absolutely, then it also is going to converge. All right, so next let's look at the ratio technique. We have learned that the partial sum of a geometric series is given by S sub n equals t sub 1 times 1 minus r to the n power over 1 minus r, where r is a common ratio between two terms. When the absolute value of r is less than 1, the series converges. And when the absolute value of 1, or the absolute value of r is greater than 1 or equal to 1, the series is going to diverge. Now, geometric series have a constant ratio between the terms. Other series have ratios that are not constant. If you remember, we looked at one just a while ago where we were multiplying by x each time, which once x is put in there, it's constant. It's not a variable like we've talked about. N is the only thing that's changing. But we had the n factorial out in front of it, so what we were multiplying by was not constant, so it was not a geometric series. That was the one that we looked at where we had n factorial times x to the n. Every time n went up, we were multiplying by one more number here, a different number each time, a greater number each time, but we were only multiplying by x here. So we were multiplying by n times x. That was your common ratio, but the thing is, it's not common. Between term 12 and term 13 is not going to be the same multiplier as between term 17 and term 18. So we didn't have a common ratio. That's what we were talking about back there. If the absolute value, the limit of the ratio between consecutive terms is less than 1, then the series will converge. Okay, so this is a good one to check for geometric series. Other series have ratios that are not constant. This actually uses for a lot of different ones. I use the ratio test a lot. If the absolute value of the limit of the ratio between the consecutive terms is less than 1, then the series will converge. So what you're going to do is you're going to choose a term and you're going to divide it by the previous term. Now you're going to use nth term expressions here, not numbers, because you want to know what's going to happen as this thing goes off to infinity. So you're actually going to end up taking the limit as n goes to infinity and finding out what this thing is. If this thing is less than 1, then the series will converge. So that's how the ratio test works. So for the sigma notation n equals 1 to infinity of t sub n, if L is the limit as n approaches infinity of the absolute value, that's one thing I've forgotten that, it's always absolute value, of t of n plus t sub n plus 1 over t sub n, then if that limit L is less than 1, the series converges, and if L is greater than 1, the series diverges. If L is equal to 1, it's indeterminate. You need to try another test. So if you do your ratio test, absolute value and everything, did everything correct, and you get 1, then you've got to do something else. You've got to go look somewhere else in some other way for a different test. All right, so let's do an example here. We got the natural log of 1 plus x, and here's our series right here. if we replace x with x minus 1, we're going to get this. All right, and if we're going to check this, when we do our absolute value, we're going to take this, but we're going to do the n plus 1 term, that's this part right here, divided by the nth term, which is this literally right here. But instead of going ahead and writing a big complex fraction, notice here, all I'm doing is keep, change, flip. Keep the top one, change the operation, flip the second one. So that's this thing right here flipped over. Now, with the absolute value, what do we know? Well, our negative 1 to the n plus 2, that's doing nothing but alternating signs. The absolute value is going to strip that out. Same thing here with the negative 1 to the n plus 1. The absolute value is going to strip that out. Now we're going to keep the absolute value around it just in case we end up with any negatives in there, but that's going to get rid of some things that complicate this thing up just a little bit. All right, so now we have x minus 1 to the n power times x minus 1 over n plus 1 times n over x minus 1 to the n power. Now, you're probably wondering, where in the crap did all this stuff come from? So what we're looking at here, this is x minus 1 to the n plus 1 power. Remember, we can split that up. If we can think about this as x to the n plus 1, that's the same thing as x to the n times x to the first. Because remember, we're just doing it backwards here. We're splitting the power up instead of combining it together. But remember our rule, if we have x to the n times x to the first, we do what with our exponents? We add. But in this case, we're working backwards again, like we did with the e to the x plus some other crap, where we'd split it up into two parts. And this is our n plus 1. Well, here's our n, and here's our plus 1. Now, the reason we're doing this is because what do we notice about the x minus n here, or x minus 1 to the n here, and the x minus 1 to the n here? Those will cancel out. Well, now we've done what? We've taken out this thing that was raised to the nth power, which makes this thing so much easier to deal with. So we're going to end up with x minus 1 times n over n plus 1. And notice, remember, we're taking the limit as n goes to infinity. So what's going to happen with our n over n plus 1? Well, that's going to go to 1. So we end up with just the absolute value of 1. So if the limit of the ratio between consecutive terms is less than 1, then the series will converge. Right here is the limit between consecutive terms. So we've got to find out when that's going to be less than 1. So we have to set this thing equal to, or sorry, less than 1, just like this. And then we're going to solve. Well, remember what you do with absolute value. With absolute value, you got a plus part and a minus part. So now we're going to solve for x by adding 1, plus 1, plus 1, plus 1. And we're going to end up with 0 is less than x is less than 2. So our interval of convergence is between 0 and 2. Now, we know that it's not going to equal 2, and we're not going to include 0, because if we were to plug this, if we plug 0 in right here, we get 0 minus 1 which gives us the absolute value of negative 1, which is not less than 1. If we plug in 2 there, we get the same thing. 2 minus 1 gives me 1. The absolute value of 1 is not less than 1. So that's why we're not including our endpoints. But you do have to check those. And in this case, the radius of convergence is 1. The distance from one end of the interval to the other is 2. Cut that in half. That's your radius. All right, I'm going to stop here just to kind of split the video up a little bit. I'm going to do some more examples and I will attach those. But this is the end of the big part of the notes in 9.4.